SP15c is pressure in fluids. So, you've seen this equation already, but this is another equation that you have to remember. You won't be given this equation. Pressure equals force over area. Units of pressure are Pascal, and the true unit is the Newton per meter squared. Alright? And thinking ahead and anticipating what they might do, because you have meter squared, another squared unit, for example, like the density with volume is a meter cubed unit, they could ask you, or they won't ask you, but they could expect you to change the units of area from centimeter squared to meter squared. So divide by 100 squared. Okay? Square the 100, not the answer. Alright? Or it could be millimeter squared back to meter squared, or it could even be the other way if they ask for it. Alright? So just be prepared for that. So this equation, the pressure, which is the force of an object on a specific area of that of a surface, could be for solids, it could be for any object in general. Yeah, if you apply force on a surface, you're applying pressure. For example, in the textbook, it shows you an image of someone walking on snow, and the best way for you to be able to do that is to have quite large snowshoes, like snow boots, if you want. Okay. And what that does is, it increases the surface area that you're walking on that surface, so the area increases, the surface area increases for the same force, alright? Because the force, if you're walking on something, the force is just your weight, it's the force from your leg on the floor. That's not going to change depending on which shoe you wear, alright? But the pressure that you apply then on the ground will change. So for the same force, a greater area will produce a lower pressure, and if there's a lower pressure on a material like snow, then you're not going to sink into the snow. It's the same example as if a camel is walking on sand. The reason a camel has such large feet, has a very large surface area on its feet, is so that for the same force that every leg applies on the sand, the area is greater, so the pressure that it applies is less. Alright, so it won't sink into the sand. Okay? So you might be expected to use this equation in any context. It could be literally someone applying the force on a wall. It could be any object applying the force on any surface. Just use the equation. Alright? But now, we're going to look at how does this equation and pressure apply for fluids. Alright? And that could be liquids or gases. Okay? The atmospheric pressure, you will have heard the expression atmospheric pressure, is 100,000 pascals. That is the pressure that the atmosphere on Earth is applying on any object, any surface. For example, right now, let's say we're at sea level in this classroom, then the pressure that is being applied on you by the air particles in the room is 100,000 newtons for every meter squared. Okay? So if there's a meter squared surface of you, then you're experiencing a force of 100,000 newtons. Okay? So atmospheric pressure is 100,000 pascals. It is due to the atmosphere of air and everything around you. You could see that as 100 kilopascals. So again, be aware that there are going to be some values in this section that could be required to be converted. Okay? The pressure in the atmosphere, so the pressure that you experience at sea level, we have adapted to 100,000 pascals. Okay? You've been in an aeroplane, you may have been to a place before which you've walked up the top of a mountain, you've been to a very high place. You can feel that the pressure is changing. Okay? You might feel quite lightheaded if you go, you know there's less oxygen as well, but you may feel slightly different if you go high. I think everybody has been in water before, you've been deep, and you felt the pressure if you go below the surface of the water increase. Okay? You definitely feel it in your ears. Alright? We are adapted to 100,000 pascals. Now for any other object that is adapted to a different pressure, that may feel like a very large amount, or not a lot. But the reason that you experience pressure, just because of the air around you, is because of the depth of the fluid. So the pressure on an object in a fluid, liquid or gas, okay, depends on the depth in which you are in that fluid. So for example, if we're at sea level, then the depth of the fluid that we're in the atmosphere, is the entire atmosphere. So go all the way to the top of the atmosphere before you leave the atmosphere and you're in empty space. All of that is right now pressing down on top of you, and obviously pressure from fluids acts in all directions as well. If you look again at the images, it's not only pushing down on your head. Okay, the pressure of the atmosphere is pushing down on your head, it's pushing your chest, it's pushing your back, it's pushing your legs, but it's pushing at right angles. Okay, so we've done this with a gas in a box, in a container. The pressure on the walls from those particles colliding with the container are always at right angles. So the pressure from a fluid always acts at right angles. okay? The pressure that you experience at sea level is due to the atmosphere, it's due to the entire atmosphere that is above you. So if you are lower in the atmosphere, i.e. you are closer to the ground, then you have more air, more fluid on top of you or acting on you, there's more weight, okay? So if the atmosphere was thinner, for example, if you went to the moon, and you were still, there's not very much atmosphere at all, okay? But on there is so little atmosphere, there's almost no particles whatsoever, you would feel very little pressure, okay? It's why you have to wear a pressurized suit, because there is no air particles above you, there's nothing acting down on you, providing that 100,000 that we are adapted to, okay? If you go higher in the atmosphere, there's less above you, there's less weight. Imagine it as a blanket. The lower you go, the greater the blanket you have acting on top of you, the greater the weight of air pushing down on you. So if you go higher in the atmosphere, then it will be less pressure, okay? Specifically, for real life examples of what actually happens and why you experience changes in pressure as a human, if we are adapted to 100,000 pascals, then we're regulated, let's say. So the outward pressure of the air, you don't feel it. You don't walk every day through the air and feel like it is pushing you. You can't feel that, you don't experience that. Because whatever is inside pushing out is the same as out pushing in, all right? We've adapted to that. Now if you go up into, let's say, the higher atmosphere, you go into the mountains or you're on an aeroplane, okay? Then the pressure that you experience up there is going to be a lot less than the 100,000 because there is less atmosphere pressing down on you. That means the outside pressure is lower. So an object such as a packet of crisps, for example, that you take on an aeroplane, you'll see them start to expand. Okay, so if you look at the picture in the textbook, you'll see a packet of crisps that has literally, it's filled with air, although it seems like it's filled with air. Okay, it's trying to push out. The pressure on the inside of that, because it was sealed at sea level in a factory, for example, it was sealed with pressure inside 100,000 pascals. But if you take that packet of crisps up into an aeroplane or to the top of a mountain, the pressure outside is much less, then inside is much greater, so outside is going to push more than, inside will be greater than out. It will push out and it fills the bag, okay? So all the particles inside are pushing out with a lot greater force, okay? Same for you. If you go up in an aeroplane and the pressure outside your body is less, technically your inside pressure is going to be trying to push out. If the conditions were extreme enough, then technically you would explode, yeah? So you go high enough, and it can happen as well. For example, if you're going in a space shuttle and you're going high enough in the atmosphere, and your suit's not pressurized, the first thing that can happen is actually your blood can start to boil, okay? Because the pressure change can cause a temperature change, and then it will overheat, all right? But you can explode. And the alternative is, if you go very deep in water, you know the pressure gets greater, okay? So because you go into water, the deeper you go, just said it depends on the depth in the fluid, the deeper you go, the more fluid you have above you pushing down. You have a greater weight. The gravitational pull on any mass above you is greater the deeper you go. So the pressure, the deeper you go in a fluid, will increase. If you as a human who is adapted to 100,000 pascals goes down into the water, deeper and deeper, okay, the pressure on the outside is going to be greater than what you're used to. So actually what's happening is it's going to crush you. You will feel like you'll start to implode. It's the exact opposite. If you go from 100,000 pascals up in the atmosphere where it's less outside, your inside will push out and you could explode. And if you go down in the water, you go deeper and deeper, the outside pressure is going to crush you, okay? There's examples I've seen before where they say there are certain fish in the sea that are adapted to very, very high pressures because that's where they live. They live their lives in very deep water, a lot of pressure. The pressure if you're in water, for example, if you go 10 meters down in water, okay, and you calculate the amount of pressure that is worth 10 meters of fluid, the density of the fluid, okay, so the three things that the pressure of a fluid acting on an object depends on is the depth that you are in the fluid, because the deeper you are in the fluid, the more there is above you, pushing down on you. The density of the fluid itself, because if you are in a more dense object or substance, okay, you will feel and experience a greater pressure. It can provide a greater force for every meter squared. All right? And obviously as a result, it's the weight or gravity as well, which depends on the pressure. All right? all right? So the weight of the fluid that's above you. Now if you go 10 meters down into, let's say, the sea, you go down 10 meters, first of all, you're going to experience an increase in pressure, okay? The fluid above you, you have 10 meters of fluid, 10 meters of seawater above you, okay? You're going to have that pressure acting on you as well as the atmospheric pressure as well. So if you're asked for the total pressure, it may say in an exam, total pressure including the atmosphere, then the pressure on you if you're 10 meters below the surface of water is the 10 meters of water above you, the pressure of just the water, plus the entire atmosphere, okay? Because while you're walking around on the ground at sea level, you have the entire atmosphere pushing down on you. You have the pressure of the whole atmosphere, which is 100,000 pascals. Plus, if you go into the water, whatever the water is providing as well. Okay, that's the total. You have the pressure of the water above you, plus the atmosphere. If they just ask for what is the pressure being applied on the object by the water, or due to the fluid, due to the liquid, or due to the water, then we don't really care about the atmosphere above. We only care about the water, say 10 meters. 10 meters depth in water will give you exactly 100,000 pascals because of the density of the water, the 10 meter depth, and the gravity as well. So you would experience double the pressure just 10 meters below the surface of water. Okay, because you'd have the whole atmosphere 100,000 plus 100,000 by 10 meters of water as well. Okay, and all the time, these forces due to the liquid, if you're in water, again, depending on which water, for example, if you went 10 meters in a swimming pool, you would not experience the same pressure as if you went 10 meters in seawater, because seawater is much more dense than swimming pool water, it's salt water, okay? You'd actually experience greater pressure in seawater than you would in a swimming pool, all right? So it depends on its density, but all the time, it's acting at 90 degrees. If you're swimming in the water, you've got 90 degrees above you on your back, you have 90 degrees from below you, on your stomach, top of your head, from in front, on your feet, from behind, every single direction, but always at 90 degrees. Okay? So the dependence on the amount of pressure that is acting on an object, or you in a fluid, is the depth you are in that fluid, the density of the fluid itself, greater density, greater pressure, greater depth, so the deeper you go, greater pressure, and therefore there is always going to be a greater weight. Okay? But technically, it's dependent on G, the gravitational field strength. Okay, so for example, if you're on a different planet with a lower G, pressure would be lower, and if you're on a planet with a greater G, the pressure would be greater. Okay? That's 15C in general, but there is another section. So it's not in the specification, it doesn't mention hydraulics in the textbook, however, hydraulics is just, it's an example of how you can use the idea of fluid pressure and the equation pressure equals force over area. Okay? So hydraulic systems or pistons, alright, we've seen pistons in chapter 14 on gas, doing work on gases. It's just an object where you apply force and it moves against the fluid. Okay? Hydraulics. Generally you would see hydraulics in engineering, for machines for example. The most basic use I've ever seen for hydraulics is brakes on a bike. If you've ever bought a bike or bicycle, you've been biking, you used to, basically as technology got better, the brakes on bikes became hydraulic brakes. So if you have hydraulic brakes, there's a little section on the brakes that is full of oil, it'll be full of a fluid, okay? And this is how it works, all right? So it uses fluids and the pressure of fluids in order to either provide force or change certain forces, okay? This is a very, very simplified version of how hydraulics work, but they use the fact that pressure is equal to the force on the fluid over the area of the container, okay? If I fill a container with fluid, and this container is small, it has a small surface area, okay? So the area of my piston, I have like a lever, a piston that I can push down into the fluid, and then I connect this container with a little gap here with the same fluid to a bigger container. So on a bike, for example, with hydraulic brakes, you have a little thing next to the brake itself, which is a small box, if anyone's ever seen it before, full of oil or fluid. It has a connecting cable to the wheel, and then there'll be another section at the bottom that can provide a force on the brakes, all right, so on a wheel. So you'll have one small, one big, all right, and you'll apply the force on the brakes yourself. Same here, you'll apply the force on this container. connect it to a bigger container. So this container has a lever here, in the same way as this one does. I push this one down, this one's going to go up. Okay? They're connected by a little section there, and the brakes is connected by a cable with fluid passing through it. But they are at the same pressure. This fluid in this container is the same as this. Okay? So in a hydraulic system, you have two sections with different area. Okay? That's the first thing. The pressure of the fluid in container 1 is the same as the pressure of the fluid in container 2. Pressure is constant or conserved between the two because it's the same pressure, it's the same container. They're connected by a little gap. You wouldn't have a greater pressure here and here if it's the same fluid. Okay? So the pressure of the fluid is constant. The pressure of the fluid in container 1 equals the pressure in container 2, which is here. So pressure 1 equals pressure 2, two different sections. The equation for pressure is force over area. So if I look at section 1 only, then the pressure in section 1 is force 1, which I apply on my brakes, divided by area 1. Okay, so F1 over A1, it's literally just use this equation, but imagine I have two sections, just the same way as we did P1 V1 equals P2 V2, so pressure and volume of section 1, and then P1 V2 for when I increase the volume, chapter 14. Alright? It's the same thing. Or the same as a transformer, for example. Current in transformer coil 1 times voltage of 1 equals current 2, voltage 2. Yeah? I1 V1 equals I2 V2. And it's the same. For example, power is conserved over a transformer. The pressure in section 1 of a hydraulic equals pressure 2. So P1 equals P2, and the equation for pressure is F1 over A1 equals F2 over A2. Okay? Now the exam question that I've seen on this, which was last summer, is explain how this hydraulic system or this piston system works in order to transfer force. Okay? So the liquid or the fluid inside, there's two sections, is at a constant pressure. P1 equals P2. If I have a small area here, alright, I apply a force myself, I push down on a piston. You know, if I push down on this piston and it's connected by the fluid to a piston over here, I push down here, that's going to go up. Yeah? If I push down here, it's going to transfer the force through the fluid, and the fluid here will push, let's say, the lid. Yeah? It will push the lid up. So I push down, the water pushes, or the fluid pushes the lid up on the other side. Alright? Fine. The point in this hydraulic system is, I don't want to push with a large force, okay? Or I can't physically push with a large force. I want to apply a force, and I want the fluid to push up on the next side, the next piston, with a much larger force. For a small force in, I want a large force out. Okay? It sounds like basically I'm only putting in a small energy and I'm creating a lot of energy out the other side, but that's not quite right. Okay? So it does obey the laws of conservation. And the reason is the area. If I start with a small area, okay, it's very easy for me to build a little system where I start with a small area filled with fluid. I apply a small force, okay? So this value, F1 over A1, is constant. Area 1 is a specific area, let's say 2 meters squared. I apply a force of 10 newtons, that's 10 over 2, that's fixed, okay? But if that's the same as F2 over A2, and I make A2 bigger, what has to happen to F2 in order to stay constant? If you have a fraction and you need the value of your fraction to be constant, because F1 over A1 is fixed, I apply a force, 10 newtons, the area that I'm applying it on is 2 meters squared, that's fixed. Okay? It's 10 newtons over 2, it's 5. Alright? Now that has to be the same pressure on the other side, because it's connected by the fluid. So 5 pascals on this side, from only 10 newtons, has to be 5 pascals. However, if area goes up in a fraction, F2 must also go up. Okay? If you have a fraction and you want both your values or the value of the fraction to remain constant, they either both go up together or they both go down together. They cannot go up and down in opposite directions or the value changes. So simply just using a small area piston here filled with fluid, connected by the fluid to a big area here, I apply a small force. The pressure that I have got in my first section of area is the same as in the second, but because the area of the second section is bigger, the force on the second section is also bigger. So for a small force in, I get a bigger force out. Okay? That's a hydraulic system. On my bike, I only want to apply a small force on my brake, but I want my wheel to feel a very big force. And the way I can do that, if I use fluids to connect them, and the fluids have the same pressure, I just need to change the area. Okay? Now the question in the exam was not, can you use this equation? It doesn't say anywhere in the spec that you're required to know this or use this. Alright? It's nice to be aware of it. But what is the explanation of a hydraulic or piston system? You have two containers with different area connected by a fluid. The pressure in both containers is the same. P1 is the same as P2. Because they're connected by the same fluid, the pressure of fluid in the first one is equal to the pressure in the second one. Because the second one has a larger area, the force in the second one, if you apply a small force on the small area, you'll receive a big force on the big area in order to keep the values the same. Okay? And that's 15c.